Okay, so this lecture will be about confidence intervals. We'll do a quick recap of everything we've been doing so far, and we'll also cover this notion of hypothesis testing, which is another of these very important aspects of statistics. And we did confidence intervals last week. I wanted to recap and go over a little bit more of examples of confidence intervals and the kind of methods we use. In hypothesis testing, we'll see um, what is called the Fisher test, and we'll also look at this very important notion of p-values, which many of you may have heard of, and so this is very quite useful in many applications of statistics. Okay, so let's do a quick recap of confidence intervals. So what was the context here? The context was parameter estimation, and here we had this distribution D, which we did not know, and this distribution had parameters that we called theta, and examples of this were things like Bernoulli of P, where the outputs were 0 and 1, and 1 was happening with probability P, which was unknown. Right, another example was the Gaussian or the normal distribution. Here there were two parameters, mu and sigma squared. And the idea in parameter estimation is that you are given x1, x2 up to xn that were all samples from this distribution D, and you are supposed to estimate the parameters of this distribution. So that's this question of parameter estimation, right? And we came up with this notion of estimators, right? An estimator is a statistic which is a function t of x1 through xn. This can be an explicit function, or this can be something that you deduce. Okay, I mean, by an explicit function I may just mean like some expression that you write down, or it can be something that is the output of some optimization that you do, right? So this is in the example of a maximum likelihood estimator. So estimators are they are functions and they produce a certain value, right? And then we ask the question, how good is the value that is produced by an estimator, right? So how good is the value produced by an estimator? And this is where we ended up with this notion of confidence intervals, right? So ideally we'd like to say that there is this unknown parameter theta, and an estimator gives you some value, and we'd like to say that the difference between these two is not too large. Okay? And that's the goal of confidence intervals, and the way we stated it formally is by saying that an alpha confidence interval estimator, alpha confidence interval for some parameter theta is a pair of statistics, by which we mean one statistic L, another U. Okay, so L is some function of x1 through xn, U is another such function, with the property that the probability that this unknown parameter theta lies between these two is at least 1 minus alpha. Okay, that's when we call this an alpha confidence interval. Okay, and we said that usually we think of alpha as something like 0.05 or 0.01, but based on the application, alpha could be way smaller. Okay. And if we said alpha equals 0.05, that corresponds to having 95% confidence in the estimate that you provide, right? So maybe there is some unknown parameter theta, and you say that okay, here is one statistic L, here's another statistic U that you can compute from data. Things only make sense when L is smaller than or equal to U. And you say that the probability that theta lies in this interval L to U is very large. Okay. And as you can imagine, you now would like to have L minus U, or I should write the absolute value of L minus U, to be really small, right? Because you would like to, the intuitive aim is to localize theta as much as possible. And what does localizing theta mean? It means that you would like to say with a very, very high confidence that theta lies within, let's say, a very small interval. Okay. So usually the goal in confidence intervals is you want this absolute value of L minus u to be as small as possible, and you'd like to have alpha to be as small as possible. Okay, so alpha is as small as possible. Because if alpha is tiny, let's say alpha is like 0.00001, then you have like a 99.999% confidence, right? Because the right hand side over here is 1 minus alpha. So that's the definitions of confidence intervals, and it makes intuitive sense. You want to you have a parameter, you want not just an estimator for this parameter, you would also like to have confidence intervals. You'd like to be able to say that it lies within a certain interval with a high probability, right? Because an estimator just gives you one value, you don't know how good it is a priori. Okay, so how do you find confidence intervals? So this we saw one general technique, and I'd like to recap that. And the idea is as you would imagine. Okay, so which is that you start off with, here's this unknown parameter theta. You start off with an estimator which produces some value. Let's call it t. Okay, and then you say that my L, I choose it to be t minus some quantity, which I'll say t minus delta. L equals t minus delta, and and then I look a little bit to the right, and then I put R equals t plus delta. Right. So if I know something about this estimator, then I might be able to say that, okay, so I find this estimator, and that plus minus delta are is a reasonable guess for a confidence interval, right? This was the kind of idea we were looking at, right? And so it's L, start with an estimator t, L needs to be a little bit smaller, R is a bit bigger than t. Okay, that's how I will choose it. How much bigger or smaller, right? So how to choose delta? Okay, and we said that one way to do it is if you have an estimate of the mean squared error of this t, right? So t is some, so recall what the mean squared error was. It was the expected value of t minus theta whole squared. So this is defined to be MSE, which I'm assuming to be equal to gamma. And suppose you have MSE of E to be gamma, and let's say you know the value of gamma. You may ask, well, how do we know this value of gamma? Often we don't know it exactly beforehand, but we can have some empirical estimates of this, as we'll see. Okay, so that's how you have an estimate of so that's expected value of t minus theta whole square. So why is this quantity relevant? So this quantity is telling us that typically the distance between this unknown parameter theta and this t, or the square distance between these two quantities, is gamma, right? And expectation, if you recall, it's like it also has this interpretation of being like the average value or the typical value, right? So on average, t minus theta whole square is roughly gamma. Okay, that's like saying on average this distance is equal to square root gamma, right? Because its square is equal to gamma. So on average this distance is square root gamma. Now the question we asked last time is that if on average this quantity is square root gamma, what is the probability that t minus theta is more than, let's say, 5 root gamma? Okay. If a quantity is like 1 on average, let's say, then intuitively you expect the probability of it being like 5 or above to be somewhat small, right? Because on average it's close to 1. So you expect most of the times it's close to 1. Sometimes it's quite large. right? So, and this is especially true, so this is true, this is a fact that is true for non-negative random variables. Okay, and this was formalized using an inequality that we saw last time, which is called Chebychev's inequality. Okay, so Chebyshev is a mathematician it's like an 18th century or 19th century mathematician perhaps, and this inequality is named after him. The proof was very simple, but it's a very useful fact. Okay, so the inequality says that if you have this property that the expected value of t minus theta whole squared is equal to gamma, then the probability that this t minus theta is more than c times root gamma. Okay, so where c is some parameter, c is, think of c as being more than 1. So let's say c equals 5. Like here I was asking about c equals 5. Then what it says is that the probability that this t minus theta is more than 5 root gamma is less than 1 by 5 squared, which is like 1 by 25, which is 0.04. So the probability that this quantity is more than, let's say if you put c equals 10, you get the probability will be 0.01 even, okay, which is even smaller. So why is this relevant? Right, so if now you plug in c equals root of 1 by alpha, okay, what is special about this quantity? This ensures that 1 by c squared is equal to alpha. Then what this implies is that the probability that t minus theta, the magnitude, is more than this c times root gamma is less than or equal to alpha. And if you take the complement of this event, right, so if I tell you that the probability that t minus theta is more than, probability that this distance is more than c root gamma is small, that's like saying that the probability that this distance is small is very high, right, or is less than or equal to c root gamma is quite large. Okay, that's what I wrote over here. So it says that the probability that so note that t minus theta less than c root gamma is exactly the same as theta lying between t plus square root gamma and t minus square root gamma. Okay, so these two are equivalent. Okay, and so this inequality with c being this value, root of 1 by alpha, implies that the probability that theta lies between t minus c root gamma and t plus c root gamma is very large. It's at least 1 minus alpha. Okay, and note that this is exactly the same as our definition of confidence intervals, right? Like if I said L equals t minus c root gamma, R equals t plus c root gamma, where c is equal to this value, root of 1 by alpha, which basically implies that t minus root of gamma by alpha. Okay, and same with the R. Then you have then that is a valid alpha confidence interval, right? So L is now a new statistic, which is the estimator t minus root of gamma by alpha. Okay, yeah, and for this, note that it's important that gamma is known. Okay, so let's plug in some values for this in the next video.